Good morning, good afternoon, and good evening. It is now top of the hour. It is 9 a.m. Pacific Standard Time from beautiful Palo Alto, California. Thank you for joining Landing AI's office hours. Today, it'll be a technical deep dive with our very talented machine learning engineer, Dylan Laird. He's been with the company since day one, so you will be getting a wealth of information. Little housekeeping. The session is recorded, and we will send follow-ups within the next business day. In addition, we encourage all questions, so please use the LinkedIn events page to post your questions, and during the Q&A, we will get to as many as we can, but we look forward to learning about your computer vision use cases. And with that, I'm going to turn my camera off and turn it over to Mr. Dylan. Mr. Dylan, all yours. Take it away.
Awesome. Thank you. Yeah, so my name is Dylan Laird, and I'm a machine learning engineer here at Landing AI. And today I'm going to go over how to develop and deploy computer vision applications. So kind of the agenda today is a couple items. First, we'll go over how to kind of define your project scope. So identifying your computer vision application and figuring out, sort of like what type of model you want to choose and things like that. And then we'll go over, once you've chosen your project and your model, how to apply data-centric techniques that you can use to iterate and improve your model performance. And then finally, we will deploy computer vision application, and I'll show you some kind of custom applications that you can find on our GitHub page and run yourself. So before we start, I'm going to need you to log on to Landing AI and create an account. And if you have a data set, ideally somewhere around 10 to 20 images, you can use that. If you don't have a data set, don't worry, we have example data sets that will be available for you once you create your project. So as you're doing that, I'll just kind of talk about some use cases here. So ever since we've released Landing Lens, we've got many use cases, everything from life sciences to automotive assembly, retail. Obviously, manufacturing has been a huge one, and maybe a little bit more recently, satellite imagery. But all of these projects, they kind of have, all of them sort of utilize the same process or best practices to build a model, improve a model, and deploy a model. So a while back, we came up with this framework. We kind of call it the ML lifecycle, but it's these sort of 4 steps that you can take to, that we use internally for building all our projects to improve and get high-performing models deployed quickly. And this is what I'm going to take you through today. So let's start off with defining a project. Throughout the presentation, I'm going to use an example project just to kind of help people follow along with. Maybe if you are on Zoom a lot, you might want to try to identify how often you look at the camera or how often you're looking away from the camera. So this is going to be a model that identifies when you're focusing on the camera or when you're not focusing on the camera. And I'll show you some applications later on that you can run yourself, maybe while you're in like a Zoom application or something like that. But you'll see these examples pop up a lot. So there's a couple of things that you want to consider when picking a project. The first is going to be what type of model are you going to want to use for this project? Is it going to be a classification model? Are you trying to do like an object detection model where you might be counting objects, or maybe like a semantic segmentation model where you really want to have pixel level accuracy on what pixel is part of what class. You also want to know how difficult the project is. So is this like a extremely ambiguous project where even humans struggle to complete this task, or is this a pretty straightforward project? And then finally, things like project performance requirements are obviously going to play a huge role. Is this something where you can't have any false negatives, maybe incredibly high accuracy requirements? Or is this something where maybe you can get away with 70, 80% accuracy or F1? And all these kind of, factors are going to determine how easy this project is going to be and what the scope and length of the project might be. And I'll go over all these in a detail here. So the main project types that we offer in Landing Lens are image classification. So given an image, you want to know like what type of picture this is. Object detection. This is maybe you want to find specific sort of objects in the image, and maybe you want to do something like count them or find the location of these objects. And semantic segmentation. So this is given like a particular pixel, what is the class of that pixel? So you can think of it as like painting a mask over an image. We also have another project type called visual prompting. I'm not going to cover this today, but you can think of this as like a very fast way to do a like semantic segmentation type project. But feel free to ask questions about that in the chat. So image classification. This is kind of the most basic project type. This is really when you want to identify image-based features that make up the entire image. So for the example on the right, maybe I want to identify suburban versus rural. And the features that constitute whether or not this image is an image of a suburban neighborhood or a rural neighborhood are very global, right? So I'm looking at big farmlands or lots of trees, minimal houses, or I'm looking at like roads and mini houses, nearby those roads. So it's kind of like this, it's not a very local feature, it's a global feature that covers the entire image. Something like object detection, maybe you want to use to identify houses. So these houses are things that can be, if I were to draw a box over a house, the house makes up most of the box. Houses are box shaped. And I might want to do things like count the number of houses on the image, which I can do by detecting the houses as boxes and then counting the boxes. I could also identify the location of the houses. So I can look at a particular box and get the location out of that. So this is probably our most popular project type and the one that people go to the most. And then finally, semantic segmentation. So maybe I want to be very exact with where I identify the box. So I don't want these kind of error regions that might get introduced in the box corners. And I want to know exactly what pixels are the houses. Or I could also be trying to identify something like roads. In this case, a road, it doesn't really fit into a box. It kind of snakes throughout the whole picture. So this would be good for a semantic segmentation type project. I just want to note here, so in this case, it's because it's semantic, I'm not going to be able to count the number of houses. The model is going to see just all of these pixels are house pixels, but you can't, it's hard to identify if a pixel belongs to a certain house. So that's where you'd want to use object detection and not semantic segmentation. So how do you go about choosing the right project type here? So if it's not obvious from the first couple of slides, maybe the project is a little bit more ambiguous. There's some other things we can do here. So I'm going to use this pill example. Maybe it's these could be Advil pills, and we're looking at images from a manufacturer of Advil pills, and they want to identify defects such as scratches on these pills. So what should we choose here? Should we choose image classification, object detection, or semantic segmentation? Well, in this particular case, you can see that the scratch is maybe a smaller region on the pill. It's more localized. And because of that, image classification, maybe not the best choice here. It's remember, image classification has to look at the entire image and get global features. And in this case, the scratch is fairly small. Object detection could be a better choice here, right? So you're giving the model a little bit more information. You're saying, hey, the scratch is right here in the middle of the pill. So it's easier for the model to learn the local region here. And in this case, semantic segmentation also could be a great choice. Here I'm painting the exact pixels that correspond to the scratch. I don't think in this case, we don't need to know how many scratches there are. So counting is not something we need to worry about, which means that semantic segmentation could also be a good choice for this project. One other consideration is the number of images that you need to train each model type. So for classification, because you're not giving the model a lot of information, I'm giving the model the entire image, and I'm saying of all the pixels in this whole image, some of them correspond to some defect, but the model, need to figure that part out. I'm not going to tell you locally where to look. And because of that, you typically need to give the model more images to learn those features. So, maybe in this case, it's 20 classes or 20 images per class. But on the other hand, the labeling effort is really low. So if you have a lot of images per class, classification might be easy. Object detection, I'm giving the model a little bit more information. I'm not saying in the entire image, find the defect. I'm saying here's the defect in the image. It's in this box region. And because you give the model more information, the model needs less images to learn the feature because it knows exactly where to look. Obviously, object detection, a little bit harder to label than image classification because I have to actually draw the boxes. But I also, on the other hand, probably need fewer images per class. And then finally, semantic segmentation, you can think of that as giving the model the most information. So I am literally specifying which pixels correspond to the scratch. So the model knows exactly what pixels to look at and exactly what class they are. Because of this is going to be the lowest data requirement. But on the other hand, this is also the hardest to label. Obviously, painting takes a long time. We do have some labeling tools that help automatically segment defects, so that can kind of reduce the time. And then visual prompting, this is kind of a newer thing. You think of it similar to semantic segmentation, but I only need to partially label an image. And it has a lot lower image requirement, and the labeling effort is pretty low. But there might be some performance trade-offs there. So for this pill project, I would probably pick something like object detection. It's a nice middle ground. I don't need to label too many images, and labeling effort is fairly low. And I'm assuming that I have at least 10 images per class. If I had fewer, I might go with semantic segmentation. I probably would not go with image classification, though. Another thing to consider is how difficult the problem is. Oftentimes when given a new project with a customer, especially if the project is pretty hard and this is the first project we're doing, usually recommend building a simpler, smaller solution first. Maybe it's a subset of the problem, maybe it's another easier problem, and try to get like a quick win early on, because it's very easy to accidentally pick a super hard problem and then the timelines get delayed and you're not showing progress for a long time. Machine learning problems can get very, very difficult, especially if you have some of these issues we're talking about, like data collection, or in this case, I'm going to talk about difficulty. There's a couple big factors to consider when estimating the difficulty, and I'll cover these in details in the following slides, but we want to look at human level performance. So if a human was tasked to do this particular job, how well are they going to do? Or maybe if you have two humans, how often would they agree on the task is a way to measure that. Object variability, so the thing that you're looking at, how consistent does that thing look, right? The more variations of that you have, the more data you're going to need to collect. Image variability, maybe the lighting or the background changes quite a lot. That's also going to affect your data collection. And then finally, performance requirements. Obviously, if it's super high performance requirements, might not be the best thing to tackle first. So the first item here is human level performance. So in this case, maybe we're looking at like a laptop or a phone or some electronic device, and you're trying to tell scratch, no scratch versus, in this case, it's a very small scratch. This is a very tricky one. It often seems kind of obvious when you first look at it, but in this particular case, what you'll find is maybe for that scratch on the right there, it's too small. So if humans were to always label that as a scratch, your overkill would be too high, and whoever your project lead doesn't want that. So humans might actually disagree on whether or not that small scratch constitutes flagging the item as defective or not. And this is super important, because if you go in and you label all those as scratches, you're going to have very high overkill. On the other hand, if you want to catch them and you label them all as okay, you're going to have a bunch of false negatives. So what we find is that if you have 2 or 3 humans do the task and they disagree with each other, let's say only 80% of the time they agree on whether or not that's a scratch or not, then your model is likely not going to exceed, in some kind of 80% accuracy, right? Because the labels it's getting are also confused. And you need to be aware of that. I think people are not, they do not often measure this, and they often assume that humans have perfect performance or near perfect performance. And if they don't, and you train a model on human labeled data, the model is going to have very poor performance. Maybe one other item here, it's also very important to analyze human performance on the same images that the model is seeing. So we once did a project at a particular manufacturing site, and we weren't able to get good performance, and we finally went to the production line and we were asking the inspectors how they were able to tell if this is a scratch or not. And they would look at the item, and if they couldn't tell, they would pick up the item, the physical item, and they would actually feel for how deep that scratch was to determine whether or not it's okay or defective. Obviously, if the model is only getting a 2D image of the scratch, you can't really tell how deep the scratch is, and therefore you don't have this information to determine if it's okay or NG. So you want to make sure that when you measure human level performance, you're measuring it on the same image data that the model is going to get, right? If you gave the model maybe some depth information, you could handle that case. So another problem that people often overlook is object variability. So if we go back to the pill scratch case, on the top, I have some pills with different scratches, and I would consider this low variability. All these scratches have a very similar texture and shape to them. And because of this, for this particular scratch, maybe we only need 10 of these or so to do this task. However, what often happens is that there's many variations of a particular defect type that you start to find as you collect more and more data. So maybe on some images there's you have a scratch. On other images, maybe it's a chip mark, maybe it's something that kind of sliced the top or it hit like a blunt object, and maybe there's like pick marks where something sharp kind of hit the pill there. And these are very clearly have different textures and different shapes than the scratch defect. So because of this, you might label all of these as scratches, but because the textures and shapes are different, when it comes to data collection and training the model, you still need, let's say, 10 images of each of these types of defects. So, because the model, it hasn't, it doesn't have the knowledge that you and I have. It's only seen the images that you give it. So if I never give it a scratch that looks like a chip, it's probably not going to know what to do with that. So this is something to be very cognizant of, when you're approaching a new project, to really dive into the data and see how many variations of the classes they have. Another very common one is image variability. So let's take the face cam. If I was going to train this model, on the top, you can see in my room, maybe I train the face cam only for me, right? And I only want to run it in my room. That's pretty low variability. I have the same sort of background. Obviously, I have the same face. I'm in the same position. So I probably don't need too many images here. However, if I wanted to run this in many different environments on different angles, you can see the bottom, there's a lot more variability there. Maybe I have a hat, maybe I have glasses on, maybe I don't, maybe I have my headphones on, maybe not, maybe there's a window in the background with bright lighting. Just like in the previous slide, these are all different textures and different scenarios that we need to show the model so it knows how to act in those situations. So if you never showed the model, a person at an angle with background lighting, it's probably not going to know what to do. To go back to the pill example, in the top case here, this is a very good setup. So in this particular case, we just took these images. We have like a white background. We have a lighting. In this case, I think it's like a round light, so you get sort of even lighting from all sides of the pill. And there's very low variability. There's no blurriness. It's always the same shape. However, obviously, if you're going to take arbitrary pictures of pills with like a phone, you're going to have a lot of different backgrounds and different angles. And it's going to be a lot harder to train a model in those situations. I think this is a pretty important fact. A lot of applications, a lot of people will spend a ton of time trying to collect data for all these corner cases. Let's take manufacturing, for example. But it's actually an incredibly time-consuming task, right? So not only do I need to collect images of the pills with different backgrounds, different lightings, things like that, I also need to collect data of the different defects with the different backgrounds of the pills in all these situations. So the data collection process actually becomes quite large when you have these issues. And oftentimes people try to sort of brute force this by improving model performance. But more often than not, if you just spend a day or two trying to standardize the lighting, maybe you buy a new lighting setup, maybe you add something to the background, play around with a few different settings, it's a lot easier to actually solve this problem than trying to collect data on all the side cases to get the model to learn it. So that's a mistake that's made quite often, where people will literally spend months trying to collect data and improve performance instead of spending maybe a week just to standardize the lighting and background. And finally, a big thing, maybe this seems obvious, but what's the performance requirements, right? So if you're looking at a project and they want incredibly high performance, you really need to add, in a lot of cases, this can be fine if you have enough data, but if you want very high performance and you only have a few defective examples, maybe you want, I don't know, one false negative out of 1,000, and you only have, let's say, 10 defective examples. Obviously, that's going to be incredibly difficult to achieve. Not only is it going to be hard to achieve with the data you're given, you're not really going to be able to test it either. Right? You clearly need more data to get any kind of statistically significant metric there. So that's something that a lot of people also kind of brush over, is what are you asking for in terms of accuracy requirements, and can you actually give me enough data to even measure that performance requirement? A lower accuracy requirement, these can be better initial projects to investigate, right? So there's a lot of projects where people ask for 99%, but in reality, if you had something that was 80% accurate, you could still sort of provide some sort of meaningful, input to the problem. Maybe if you're counting houses, right? If you're doing it in aggregate over many images, you don't necessarily need to be 100% correct there. You only need an estimate of the number of houses. Okay, so I hope by now you've been able to make a Landing Lens account. So I'm going to exit out of the slides here, and I'm going to go over, and you should have a page similar to this when you log in. And you can go over here to create project. And this is going to make a new Landing Lens project. And I'm going to call this Dylan's Face Focus project. Oops, and I can't use quotes there. And don't worry. So if you don't have data, if you do have data, you can drop it here and upload it. If you don't, you can load some sample data, and you can click on that load sample data and click on Face Focus labeled. And this is going to load in, let's say, 20 labeled images for you. So these are all images we took of some people, and they're labeled. This person's facing the camera or facing away. This is facing the camera. And I can also upload some of my own data. Since I'm going to run this on myself, I want to make sure I have images of myself to train the model on. So I click on that top right icon there, and I can turn on webcam. I'm going to take one picture facing, and then one picture facing away. And cool, so I've uploaded 2 images here. And let's see if those, you reload the page. Yep, there it goes. And then I'm going to label these. So up here in the top left, I'm going to click facing away and label my face. And then I'm going to go over to the next image here, and this is facing. So I'm going to click facing camera and label that. And then I'm going to go back, and once you've labeled some images of yourself, you can go up here to the top right and you can click train. And that's going to, behind the scenes, launch a training job for you. This is an object detection model that the Landing Lens team has chosen for you. And we've done a lot of hyperparameter tuning on this model. And sometimes it does some live hyperparameter tuning here. to kind of pick the best model for this particular problem. You're going to see the loss curve on the right there. I'm going to step away from this for now, and we'll come back to this in a bit. So now I'm going to talk about collecting images, and I'm going to talk about image quality and label quality. These are two very important factors that you want to sort of think about when you're collecting images, because they're going to have a very big impact on your model, especially when you're doing your own project and you don't have, thousands or hundreds of thousands or millions of images. Label quality and image quality have a much higher impact, right? If I only have 10 labeled images and 2 of them are labeled ambiguously, or the image quality is bad, there's 20% of your data. Deep learning models, they tend to overfit. So they're not going to know that 20% of their images are bad. They're just going to learn what they are. So, when we're looking at image quality, one of the things we see is, sort of camera focus. In this case, it's a little bit extreme, but you'd be surprised how often, especially when you're looking at very, very small features, things like camera focus, the whole object might not be in focus. And so this problem actually pops up more often than not. But clearly, if your camera is not focused or not focused in a particular region, it can be very difficult to distinguish the thing you're looking at from something else. So in this case, it's a reflection, right? It's kind of hard to tell. I certainly can't for the middle and the right image if those are reflections or if those are actually scratches. So again, like going back to your lighting and your image capturing system to improve image quality can be a big thing. Or if you know that your camera, is only in focus for a particular range, you may just need to live with the fact that you cannot find defects outside of that range, right? So you either need a different setup or a different lens or something. Maybe this is a little bit more common. So in this case, this is actually a real project. We're trying to detect boats from satellite images. There's kind of 2 problems here. One is the resolution might not be high enough. If it's a really small personal boat, that's really only going to take up 10 pixels or less on this image. And that can be very, very difficult, especially in satellite images where there's quite a lot going on, to distinguish a boat from something else in the image. You're also going to have, things occluding the boat, right? Like a tree or a shadow. So this alone, if you're trying to look at like 100% accuracy on boat detection on satellite images, just because of these 2 facts, that doesn't seem like a very reasonable performance requirement, because there's just, there's no way the satellite can see underneath a tree or a shadow or detect something that's, maybe only a few feet in width. So, these are things that you want to look at. Maybe for this particular case, for really small boats or occluded things, you're going to say those don't count towards my boat detection task. Finally, we'll go over label quality. This kind of harkens back to the human level performance that we were talking about before. This is by far the largest contributor to poor performance in projects that I see. It seems, I think it's such a huge issue because it seems very minor. Most people, when they're labeling, they think they can label pretty consistently. But oftentimes labeling consistency is actually a very difficult task. So I see this quite a lot, and I'll go over some examples of where I've seen this in real projects later on. But for this particular case, particularly if you have a couple labelers, the green boxes, they might all be labeled consistently, but for those red boxes, the pick marks, you might see some labelers label them as defects, and other labelers not. Maybe they leave it unlabeled. These things, again, they can really confuse the model, particularly when you don't have a lot of data. And these are more often than not the biggest contributors to your model's poor performance, is these little inconsistencies in labeling. So this is an actual project where we saw a labeling inconsistency. So in this particular project, we were trying to segment roads, which at first sounds like a very easy task to do. I think everyone knows what a road is, and it's probably not very hard to label roads. But after we looked through all the labeled data here, you can see that even in the same image, so this must be for the same labeler, they get confused. So there's all these little side roads, and there's things like parking lots. Like, do we label the parking lots as roads, or do we not label it as roads, right? And someone has to look through all this data and make some call on whether or not you want parking lots labeled as roads, and make sure that your labeling team labels this consistently, or just you label it consistently. Cool. Okay, so I'm going to go back to our project, and this is done labeling. And okay, so this one, we got 100% performance here. This is a fairly straightforward task, but you don't always get that. I usually don't get 100% performance. But from this page, you'll notice a few things here. So you're going to have deploy and predict up here. You can click on an image, and I can see here that the solid box is the label, and the dotted box is the prediction. So it's predicted correctly here. And I can go to the bottom right here, and this is where you're going to see your confusion matrix in column form or row form. So they're all correct, so we're not going to see any issues here. But so this is, the ground truth was facing camera and the prediction was facing camera. And I can actually, if I wanted to do some error analysis here, I can click on these images and I can see, where these predictions are. So if there was an incorrect prediction, I could go in there and quickly sort through the images to see those. You can see when I clicked on that, it applied a filter up here where the ground truth is facing and the prediction is facing. I can just click that X there to go back. And you can also see this change to instance view. So this is looking, each image you see here is of a particular bounding box. So I can go back to image view there. And I can see the original images. And if you want, you could click on predict, and I can take an image here. And you can run the model really quickly and just give it a quick test to see if it's if it's running correctly. Okay, so great. So there, it's predicted facing camera. You can also see here, you can change the threshold. And as you change the threshold, you'll see how the false positives, false negatives start to trade off. Right, with a lower threshold, I would expect to see more false positives. It's the yellow line here. Higher threshold, I expect to see more false negatives. That's the yellow pink line there. Okay, so now I'm going to talk a little bit more about some of the details of training. One thing that I think is probably the most important item here is you want to deploy really early on. So a lot of people like to wait until they have a high-performing model to deploy. It's really a bad choice. Oftentimes you don't have enough data, or the data that you're actually deploying on has a slightly different distribution than the data you're testing on. What you want to do is deploy early and in a safe way. So in manufacturing, what we often do is you usually have an inspection line or something that's already set up, right? So someone's already checking for defective items. It could be a human, it could be another automated system. And what we'll do is we'll deploy in shadow mode. So we'll run the model, it'll be predicting okay and defective parts, but it's not going to affect the production line at all. So there's really no harm in deploying it early. And we do that to kind of gauge two things. A, how close is that test distribution to our training distribution? So usually the test distribution looks a little bit different and we got to collect more data. And B, B is just collecting more data there. And these are like very data-centric AI approaches. You're running it on new data. You're looking for side cases, edge cases that you didn't have in your training set. You're collecting that, bringing it back, and retraining your model. That should be your kind of main mechanism for improving model performance, is collecting more data and cleaning labels. That's usually your, if you can think of different levers to pull to improve model performance, it's going to be your biggest lever. That's going to be where you can get most of your gains. Where most people like to focus on is hyperparameters and let's say model architecture type. This is more often than not going to be your smallest lever. Usually you're not going to get any kind of meaningful difference tuning these kind of hyperparameters, with the exception of data augmentation. That can be a very important one. Sort of also ties into data-centric, because you're looking at different augmentations of the images. That can be a good kind of lever to pull there. So now I'm going to cover, this is when I go through a project, this is kind of the first sort of things that I look at. So I'm going to assume here you've trained a model, you've evaluated it on some kind of holdout test set, and you're looking at that test set, and let's say you see a particular false negative. So in this case, on the right here, you can see my mouse, the model has gotten the scratch, but I wanted it to get this pick mark, and it's missed the pick mark. So I've trained the model, I'm looking at the test set, and I see this issue, right? There's a false negative, it's missed the pick mark. The first thing I do is I go back through the training set and I look for features that are similar to this pick mark that it missed in my dev or test set. And very often, either I or another labeler has forgotten to label this exact feature, and it's usually maybe a more rare feature. Maybe there's only like 3 or 4 of them. So this is the first thing I do, and this is a very common root cause for false negative errors in your test set. It's usually because you mislabeled something or you forgot to label something in your training set. Really easy fix. Go through your training set, look for those features, and make sure they're labeled. Another common one, this is a little bit more rare, but it can be kind of a gotcha. So usually when you split your train and dev, it's random. I wouldn't want to spend time splitting it manually. That sounds like it would take too long. And sometimes if you have particularly rare features or rare classes, it can be the case that an abnormally large amount of those end up in a dev or test set. Now, if you have them as separate classes, Landing Lens will auto split them for you, and it'll make sure that those ratios are correct. But like we saw in the previous case, often under a given class, you can have many variations of that class. And obviously we can't tell how many variations are under the class if you've labeled them all as the same class. So some of those variations, they might all end up in your test set or dev set. So sometimes if I'm seeing a false negative in the dev set, I'll go back and look through the train set. But it could be the case that instead of finding that I haven't labeled this feature, I just don't find the feature at all. And all the features ended up in my dev set. I simply just make sure that that particular feature is split more evenly between train and dev. And if you have a holdout test set and they're all in the test set, you may need to talk with the project lead. You may need to, resample a new test set, because obviously if the model is never going to see that feature in train, you can't expect it to perform well on that feature in test. This is another one, kind of similar to the first false negative example. Sometimes I'll see a false positive. So in this case, this is a true false positive that we found in this data set. This was the road labeling example. And this was a picture of some dirt roads. And in this case, it predicted a road in the middle of the woods. When I didn't want it to predict dirt roads. So I went back and I looked to the train set and I noticed that there was a lot of images where people had labeled dirt roads. So that's, again, that's like a labeling ambiguity. You have to go back, look through your train set and make sure that it's labeled consistently in the way that you want it to be labeled. This is obviously, to fix this, you just simply remove the label and retrain. And then finally, this is kind of very similar to the dev set example that I just went over, but in this case, I may have a couple examples in my dev set where I'm like looking away from the camera, and if I didn't train on those images, the model is not going to know what to do there. So in this case, you can either move those images back to some of those images back to the train set, or better yet, if you've deployed early on, you should be collecting a lot of these kind of new data, and you can move those into your train set to fix this issue. So just by simply deploying early, you're collecting more data to improve model performance on cases like these. Okay, so now I'm going to show some let me answer a few questions here. I see there's some more questions on the slide. Is there any LLM use case LLMs used? Not for the cases that I'm going to cover today, but at the end I can maybe mention a few LLM use cases that we have with other projects. Can we know the layer architecture used in this model? Yeah, I think so. For the object detection model, we're using it's like an anchor-free type object detection model, and we've done quite a lot of tuning and a hyperparameter selection. So internally, what we do is when we choose a model, we collect a bunch of data that is similar to our customer's use case. So it's more so in like manufacturing satellite imagery. It's not going to be like your typical ImageNet detect the cat dog type images. And we build these internal benchmarks. And then we test out different architectures and we tune different hyperparameters for these data sets. And we kind of look at different data set sizes. Typically, like our customers are dealing with smaller data sets in the tens to hundreds to maybe 1,000 range. Whereas like in academics, you'll often see millions to tens of millions. So it's a very different regime, and you need different hyperparameters and different schedulers to handle those cases. During the presentation of quality images discussed, I had a general question that's a little to do with the presentation in regards of medical images. When we only have very low image quality that have low resolution, what is your suggestion to increase image quality? So that's a good question. So this case, you only have low resolution images to do your task. So you have kind of a signal issue here, right? If you have noisy data, there's only so much signal that you can get out of that. I think it's very important in this particular case to medical images can be a little bit weird. Sometimes models can do better than humans, but I would definitely do a human level performance kind of test to try to better understand how much signal is actually in those images. I think people in this particular case might be tempted to use machine learning to upsample the image quality or to generate synthetic images, but you have to be very careful there, right? If you start with, let's say, X amount of information in that image, and you try to upsample it to get Y amount of information where Y is greater than X, that could very easily be hallucinated information. That's not at all relevant to the original information in the image, which is going to put you in a worse place, right, than you started with. The only time that synthetic data might work there is if the model that's generating the synthetic data was already trained on many high quality examples. So the model itself has more information about what's going on with these images than the images do. Okay, I'm running a little short on time here. So let me quickly go to the model analysis page. So this, I'm showing you a new project here. This is the satellite project. And for this project, it's different than the one I was just showing you with the face stuff. This is going to be, this is a semantic segmentation project, and I'm trying to segment out the roads. And so I've trained a semantic segmentation model to do this. Now, after you've trained the model, you can go over to the left here and you can click on this models page. And this is a new page we released. What you're going to see here is your different training runs and your performance across sort of different data sets. And so this was the first model I trained here, trained it a while ago in January. And I can go here and I can click on the dev set, and it's going to pop up this window here. And because this is a semantic segmentation model, the metric we're looking at here is IOU, this intersection over union. So it's, if I have a ground truth mask, this is the intersection of the ground truth mask with my prediction mask over the union of those two masks. So you can think of it as overlap. And down here, I can see on the left column, the ground truth mask, and on the right column, the mask that the model predicted. And I can click on this, and I can see these masks here. I'm not exactly sure why they're not showing up. And then I can go here, and I can also, this is going to be my row-wise confusion matrix again. But in this case, instead of false positive and false negative boxes, I'm looking at false positive and false negative pixel counts, right? Because this is a semantic task and I'm predicting pixels. And from here, I can see of the two error categories, the false negative is the larger one. So I can click on that and I can go down here. And now what I'm going to see is on the left-hand side, it's going to show me the mask difference. So the thing that's highlighted on the left side there is going to be the error area. This is the false negative area. I've clicked on the false negative number and I'm looking at the false negative pixels. And if I hover over it, it's going to go back and show me the original ground truth and prediction. And you can see here that it's missed the parking lot, right? Just like we were talking about before. So in this case, my biggest false negative example is where the model didn't detect the parking lot. And this is an actual project that we actually ran on some actual labeled data, and this is an actual error. So these are very, very common kinds of errors. So now that I know this, what I might want to do is go back here and go back and find all my parking lot examples. Now, I've already gone back and relabeled these, so bear with me for a second. You just imagine this was not labeled. and I can add in tags, and I can tag these as parking lots. And this is what I do quite a lot to keep my data organized and keep my kind of side cases and error cases organized. And if I wanted to, I've already gone through and tagged all these. I can go back here and I can, sorry, let me, do not disturb. And I can look at all the parking lot examples that I've tagged. And if I want to, from here, I can select these images and I can make a snapshot. And what the snapshot is going to do is it's going to take all the images I've selected and freeze them. And then I can use these later on to evaluate. So in this case, I've got a snapshot of cul-de-sacs, I've got a snapshot of railroads, and I've got a snapshot of parking lots. And then, like I said before, so I went back, so we did this, we found out we're missing parking lot examples. We have false negative parking lots. We went back to the data set. I tagged all the parking lots. I made sure they're all labeled. And then I made a snapshot of those parking lot examples so that I can evaluate on parking lots later on as I improve the model. So that's what this column is here. This is the parking lot snapshot that I just showed you. And you can see on the original model, I'm only getting 31% IOU. Now, after I went back and I relabeled those examples, this goes up to 51% IOU. And you can see here, this is the same exact example we were looking at before, but now the model's getting that parking lot labeled. So this is a much more effective way to improve that performance. You can see here my false negatives are now the lowest error, the false positives are higher. Then if I were to go back and try to tune the hyperparam, maybe tune the learning rate or change a different architecture, this is a much more direct way to improve the exact error that you're looking at. So I know we're running short on time here. Let me just go through this next section here on deploying, and then I'll head over to questions. So yeah, finally, after you do this, you're going to want to deploy your model. Yeah, really stress deploying early on to try to collect more data. And you can do things like monitor the performance of your data or the performance of your model in production. If you don't have ground truth, that's also fine. Oftentimes you don't when you deploy. What I often do is I'll measure, let's say, defective predictions. So on a manufacturing line, I already know that there's not going to be a lot of defects. And maybe I have a rate in mind. Maybe it's like 1 defect per 1,000. And so if I see the defective rate spiking above or below that prior rate that I know, then I will sample that data and look at that data, right? So let's say on an average day, I should expect to see 1 defect per 30 minutes or something. And as I'm monitoring the model, maybe there's 1 30-minute period where it shows 50 defects per 30 minutes, which is way higher. That's the data that you're going to want to sample and look at. This happens all the time. I mean, we were doing a project not too long ago where we were monitoring some video data for this particular compressor item, and suddenly the defect rate shot way up. We looked at the data, and it turns out some inspector had put a broom in front of the camera. And the model thought that the model's never seen a broom before. It kind of looks like a defect. So it thought that was defective, and we had to collect a lot of broom data to retrain the model. Mustafa, just to answer your question. So if you look at the rate of your class predictions and they don't line up with what you're expecting, that's how you can tell that your model's not doing well. On the other hand, if you have a system where you're in shadow mode, let's say you have an inspector and they're already classifying each image as OKNG, and you have a way to collect that, then you have ground truth, and you can just tell exactly when the model's not doing well. If not, you can rely on rates, prediction rates. Cool. So let's just do this here. Let me go back. Oops. Oh, I should have clicked on this thing. Oh, darn. I clicked on the wrong button there. But here's another project. So when you've finished training the model, you can click this deploy, and you can go. It'll pop up this screen, and I've already deployed a model here, so I already have an endpoint that I've deployed to. But if not, you can make a new endpoint there and click deploy, and then you can go over here, and in this particular page, you'll see where your model is deployed. You've got the same predict button that we saw earlier, and you can also copy an endpoint here. And if you check out our GitHub page, this is landingai-python. You'll see examples of how to call your deployed model with your API key and your endpoint ID. And then you can write a program to do this this model prediction. And that's it. Yeah. So definitely there's some links here on where to access the GitHub page. We have lots of tutorials. And if you make your own Streamlit app or something, feel free to share it. And let us know about it.
Thank you, Dylan, for a spectacular presentation. To our audience, we are now at top of the hour, and we're going to go ahead and close this out, but we're going to take at least one more question. Dylan, we are using Jetson. Is Landing AI a peer?
Yeah. So Jetson, I'm assuming you're talking about like the Jetson Nano. That's like just to give some more context, that's a NVIDIA GPU device that's kind of small and can run. This is cheaper than like a H100 or something. We do have an option to deploy offline, so you can download the model and deploy it wherever you want, including a Jetson, which we've run on many times in many different projects in the past. So that's a great device to run landing lens models on. Very, very commonly used.
Thank you. Great answer. For everyone who posted questions, we will be sending a follow-up tomorrow with the presentation slides. In addition, there was a question around getting one of our engineers to talk at one of your events. We'd welcome that opportunity. It takes a little bit of coordination, but I will make sure to follow up with you. One thing I would definitely invite everyone to do is join our community. Dylan, if you can take me to that slide real quick. In addition, sign up for Landing Lens, get active in your project. We have an entire team that will support you. And I also invite you to take advantage of our no-cost consulting with a Landing AI CV specialist. It's an opportunity for you to share your use cases. We've been having many of these sessions since we started offering it, and we're getting some great questions and some great use cases. And it's giving an opportunity to talk through what you're looking to implement and see what we can do about best practices and what makes the most sense. So please, that invitation will also be in the email, but if you want to go ahead and take a snapshot of Schedule Today hyperlink, please do get on our calendars and we'll chat soon. With that, thank you everyone for your time today. Dylan, again, a great presentation. To our audience, we appreciate all the great questions, and for those that we didn't get answered, we will definitely do a follow-up. Have a great day, everybody. Enjoy your Wednesday. Goodbye.
Thank you.